Okay, it's live.
Okay, great. So, students, welcome to the Hangout for compilers. We have both TAs, Adam and Chow, and myself here. And we'll start with some announcements. So, first announcement is about the project phase one. So, we decided to give you guys a little bit of extra time to handle the nitty gritty details, especially on the IR code generation side, if because some of you might have asked for some time. So, this is what we are going to do. Um, so, Chow, can you mute, please? Because
Oh,
it's okay.
sorry.
Yeah, no problem. So, this is what is going on. So, first, we'll give you some extra days till submit till um, uh, Monday, end of Monday. That is Tuesday morning, AOE time, um, uh, to finish off some IR code generation if you are behind, or to tighten it and make sure that it is all correct. And go ahead and then submit your project phase one. So that will be your new due date at 7 a.m. on Tuesday, AOE time, um, which will be 7 a.m. EST um, on Tuesday. So that will be the due date for submitting phase one. And Chow is posting an announcement about it. Second is we'll also allow you to improve and resubmit if you would like the IR code generation part, and we'll give you a new due date for just revising and resubmitting it in case you need a little bit extra time for that. Now, that is strictly optional, of course, that is not with any penalty. We want you to wrap up phase one by Tuesday, of course. We have already given the phase two, which you can get started on. So, but if you want a little bit time to clean up even after Tuesday, will allow resubmission till a new date without any penalty, and we'll use that. That is as far as phase one is concerned. Phase two, along with the template to read the IR. So let me now talk about phase two, which is about generating the code. So first you have to generate a very simple code, doing just the instruction selection and native load stores before from the uh, IR. What you will do is you will load the operands from the stack into registers using loads, then operate on the operation of adding the two or subtracting or whatever the operation is, and then you'll store it back onto the stack in terms of the temporary, and then keep doing this. So first, I suggest you just implement simple arithmetic statements and assignment statement. So first complete that, no control flow whatsoever. Then you can implement simple control flow in terms of the branch and so on, if then else kind of thing. Then you can go for loops and then complete all the control flow operations. And then once you're done with that, you can do the arrays. So that is the order which we have suggested in the document as well. And so get this native code generator done. So you'll get a final working program out of your Tiger program, which will be, of course, quite inefficient because it will have lots of load stores. It will operate out of all the memory locations, and you run it through the MIP simulator. The TAs will be giving you that, and then generate the results in terms of number of dynamic instructions and so on. So that will complete first part of phase two. The second part, which is on the register location side, you have to do control flow graph detection, a simple algorithm there, um, which you have to implement. Then you have to implement liveness analysis, and then interference graph, and then do the brick style register allocation. So the second part is a little complex. I suggest uh, you take care of the first part very quickly, and then keep good bit of time, at least I would say 3 weeks in hand for part, 2.5 weeks for the second part. Um, Not 3 weeks, but 2.5 weeks should be good for liveness and register allocation and making the whole thing working. So that should be your budgeting. And in order to give you some practice about the live range concepts and so on, we have a homework uh, on a simple example, uh, which is what you can also use as a test case for testing your register allocation, and then tally the results with what you have gotten by hand. So whatever you are going to see there is will be your reference point of live ranges and how the webs and all look like, and that will help you to debug some things when you actually implement them too. This concept is very important and will also help you prepare for finals. So that's about the homework 3, which is just released. And I guess in terms of grading your project phase 1, we'll go ahead and grade it and give you the grades back before your drop date so that you'll know where you stand. And I guess that's all I have to cover here. You should be now in the middle of studying the register allocation topic, having finished control flow graph detection, live range analysis you should have done. So I want to talk a little bit about that to clarify any doubts you may have. So this is a very interesting backward analysis. After the basic blocks are detected, what we do is we find out uh, what is live at the beginning of the basic block using the information of what is live at the end of the block. So first of all, at the end of the program, nothing is live. So we start with an empty set, and then whatever values are used in a basic block, they become live at the entrance, and whatever values are defined in the basic block, they become dead at the entrance of the block. And so those are the two concepts which are nicely covered in the lecture videos through examples, and you can practice those and find out the live ranges working backwards. The algorithms converge, and then you can merge the live ranges based on the common uses and definitions that they share and form webs. That is our next lesson, which is you will be pacing, I think, in the next week, or you might be pacing in this week. I think the two lessons are being paced together, which allows you to form the webs using the live ranges. That's the next thing, and then their interference graphs. So it should be pretty easy to understand. If you run into any questions, please use Piazza or ask here. And then building the interference graph and doing the selection from there is what is the Briggs heuristic is optimistic one, which we have asked you to use, and that is what you will have to implement in your phase 2. So that is, these lessons are very critical. So if you run into any problems, ask us. Other than that, I don't have any other announcement. um, Chow or Adam, do you have anything to add or announce?
Homework 2 grading has started. I expect it to be done in just a few more days. That's it.
Okay, great. So homework 2, yeah, we'll have homework 2 returned to you in next few days. Adam, probably early next week. Is that what you're aiming at?
Yeah, that's pretty safe. I'm heading out of town this weekend, but I should be able to knock a few more out. I would say Monday or Tuesday to expect them.
Sounds great. Thank you, Adam.
Uh,
And
no from my side.
okay. So some of you had expressed concern that the pacing is a little bit hectic in this semester. Unfortunately, our summer semester is short by almost 3 weeks, and that's about 3 out of 17 weeks is a good bit of time, almost 20% less. So we do have to compress some things, and unfortunately, because of that reason, I do agree with the fact that the more time could have been desirable between the lessons coverage and the use of that, especially in a project. That's why we are giving you a little bit more time in terms of implementing the IR code generator. Um, Unfortunately, to see everything completed in a semester and get a working compiler is the only way it will allow you to see the whole big picture of how these phases interact and what really happens and how the code is generated and so on. So we really cannot leave out anything here, and we have to unfortunately do this, which I also don't like. And I agree with the sentiment expressed fully, and I understand. So that's why we are giving you some more time for IR code generator, especially that part, which should not be difficult to implement if you had followed the lecture videos. It is basically pretty straightforward algorithm. And once you're done the semantic analysis, which is going to follow those three traversals and listening classes, you can just piggyback on semantic analysis and do the IR code generation. So that's pretty much how it will work. So it will keep descending, for example, in a AST, and it will go to the leaf nodes, check their type compatibility, etc., the availability of the operands in the current scope. If there semantic errors take place, then we will suppress the IR code generation. We will not do it. But if there is no semantic error, we will go ahead and then generate a temporary there and send it up to the level from where we came up from. And we'll keep doing this as far as um, the short circuit operators are concerned. They will be dealt with as far as the control flow is concerned. They will be dealt with exactly as shown um, in the semantic analysis phase. And hopefully, once you have understood it and implemented it nicely, the IR code generation should exactly follow similar places in the code. After the checking is done, you actually go ahead and generate the order of traversal is exactly same, and um, generate temporaries and send them up, combine them, and those algorithms are not complex. Again, I want you to test those on simple examples which have only probably um, expressions and assignment statements. That's a fair thing to start with. No control flow. Then you may want to add the short circuit operators and check those are working fine. And then you can go and do the if then else and then while loops and so on. So it should hopefully be not too difficult. And again, my suggestion is do it step by step and see how things are going. Hopefully, the book for Antler that we have given you and the references there, especially how some calculator is implemented and some other thing is implemented there, will help you to quickly design and implement these listener classes and tree traversals. And I'd like to ask if T has have any comments on these, or because some of them, I mean, Adam has done this class earlier, so if you want to chime in, I am Adam, and say a few things, words of wisdom for them.
Oh, sure. One thing that I would definitely not do is don't get too caught up in the details of either the Antler book or the textbook. There's a ton of information, and it like both books really are deep dives into these subjects. For Antler specifically, just learning how the built-in listener works and learning the different components that Antler gives you, the parser generator gives you, these abstract class blueprints and these interfaces. If you learn how to just tie into those, that's really all you need to do. Then you can get creative as to how you want to actually build your parser itself. But you can definitely get yourself bogged down in the details from both of those books. So just read with caution, I would say.
Great, great words of wisdom. So absolutely, these books are meant for, especially Antler, is meant for professional compiler developers, and that's why they have to give you all kinds of details and complexities are there because this Antler is really used in, writing very complex languages. For our purposes, just focus on what you need, and I think Adam has said it in the right way. That just focus on how these interfaces and abstract classes are offered to you through the infrastructure, and then just using those as hooks. You got to develop your own code quickly, and then do not worry about the rest of the complexities which may be present, which may be of super helpful if you're writing a professional compiler, of course, as a part of the team, and where you have many more resources and time, and you're doing this for living. That's totally different affair. Cooper's book is a little bit similar. It's written by a total expert on this subject, and it does go well beyond what we covered in the class. I gave you some of that reading just for a cursory reason. It is not expected that you delve into all kinds of details there. As you can see, our homeworks and other things are pretty pertinent to what we are taught. To just broaden what you know, I expect you to read that, but cursorily, of course, whatever is covered in the lectures, I think if you read it from the book with the examples and algorithms, it will definitely help you strengthen your knowledge and concept. And that's what you should do. But going beyond that is a little bit of a, um, what I should say is as a um, optional or is not really fully expected exercise, and do it as per your timing issues and read it somewhat and leave it. So that is, I think, applicable both in terms of pacing the book and definitely using Antler for your project. And the traversals and all that, semantic traversals. Adam, I wanted to see if you have anything to say about interleaving between the semantic analysis and IR code generation. Any hints you want to give them in terms of should they be doing this together or one after the other? And the traversals, are they different or the similar?
They're all pretty similar, but I handled them all differently. The way, I mean, I handled them all separately, I should say. There were three major components in my implementation, and they all kind of operated by themselves. So you had one that checked types, one that checked scope, and then one that generated IR. The overall idea was that my implementation had this hierarchy of abstract and concrete classes. And at the abstract level, all three of those components were defined, and then of course it just passes through to concrete implementations on concrete classes. Most of the time, I think I can say all three of those components are simply pass through. So you call one from, say, the expression level or the statement level, and it does nothing but pass through to the constituent parts that make up whatever expression or statement you're currently evaluating. So I think the big idea was semantic analysis is mostly about checking type compatibility and scope compatibility. So that really becomes the only thing that it has to do. Just let the let the Antler tool build your parse tree, build your hierarchy of class objects of object instances, and then run through once to check types, run through again to check scope, and then run through one final time to generate IR. I thought about trying to combine them just for the sake of efficiency, but uh, I think it's also important to remember that Tiger is nowhere near a production level programming language that any of us would ever use in real life. It's way too simple, and I think it's very easy to forget that and think that we need to support all of this kind of modern functionality that we see in our day-to-day jobs. We really don't, and because Tiger is so simple, we can afford to make some sacrifices in performance and do type checking all by itself, do scope analysis all by itself, and then generate IR all by itself. So that's the approach I took.
That's fantastic. Thank you for clarifying that, Adam.
Sure.
Yes. So I think one he made actually two important points here, which I would like to kind of just put it in front of you in a slightly different way. So first of all, design simplicity is really key here, because when you develop any modern software, you want to make sure that you are able to develop something and test it, debug it, and then move to the next phase. So you can see here, by doing this approach in three different phases, so to say, or passes, he has been able to maybe make sure that each pass or traversal on the tree is kind of nicely checked and debugged thoroughly with regard to the scoping, with regard to the typing, in terms of semantic soundness, etc. And then finally is lowered into the last pass, which is IR code generation. So that is a very clean and nice design. I like it. Okay. So I think I recommend something similar if you are still designing or doing it. And the second thing I really liked is his comment about not worrying about, this is not really a production compiler, and it's not a huge language, and the performance efficiency of the passes, where they should, if you combine them, you will get very high performance. But don't worry about that, because first of all, it will never get used that way, and it is better to go for such a modular design than focusing on performance, because I think the team design, the compilers are designed in team, nobody designed it solo. And typically you will see such one team dealing with maybe IR code generation, second one is dealing with semantic analysis, and though typically um, uh, separation of concerns or design like this are really done in a real setting. The small loss of performance on modern high performance processors is really negligible, even if the language is large or if your programs are large. And then once things are stable, maybe some optimizations are done to remove some redundancies or merge passes and all. But that's much later stage in the design, and we of course don't have anything like that in this class. And the Tiger being such a simple and nice language, you definitely should focus on simplicity and getting the job done, not through a hack. So be principled here, because if you adopt hack approach, you will yourself land in trouble. So do follow the principles which are given in the slides, in terms of taking the operands, checking them, looking at their attributes, holding the attributes properly in symbol tables. Follow all that norm, because it's important to do it. Don't try to short circuit and pass values around and here and there, because such hackish approaches is the lead cause of bugs and errors. And avoid that. It will save you yourself some time in debugging. And follow the design principles approach and keep it simple and clean. And once you do that, I think this should probably be turned around very, very quickly. We are hoping that most of you are done at this point. We're just giving little extra time to take off that pressure or lead, which some of you have experienced, because there was not much gap between when it was spaced and when it is due. So we'll allow you a little bit of more time to help you out that there. But other than that, don't overly spend time on this, because it's not supposed to be extremely complicated. And we are not scoped the project that, hey, it will take you like 24/7 for last 15 days to actually finish our phase one. That's obviously not the amount of effort that is expected here. Adam, you want to comment a little bit about the LOC's expectations, just to kind of shed some light, phase one, in terms of how many LOCs you had? And I believe you guys implemented not with Antler, so it may be slightly different, right?
I used Antler. I'm not sure, exactly how many lines of code. I can tell you that I would say most of my functions were very short. So I had a large number of very short focused functions. And then at the end of the day, I was really just trying to develop something that would make sense. I mean, to be honest, I put a lot of trust in the TAs,
Mhm.
hoping that they weren't going to be checking exact things. And we aren't. I know Chow. I think Chow is taking point on grading the project one, and I don't. I don't get the impression that he's looking for an exact fixed um, output. I mean, accurate output, but these aren't being auto graded, is what I'm trying to
Yes,
say,
yes,
and
yes,
that's
yes.
been
So
brought up
yeah,
before.
so we are not sacrosanct on the exact format of IR or exact details of the IR. We want the IR to be correct, first of all, and all the checks to be done in terms of soundness and so on. So if you throw a program at it which is unsound, where something is not declared or is not compatible, of course we expect errors and other things to be reported. But for sound programs, there is small flexibility there in terms of how you generate the IR and so on. Keep some additional annotations. We are definitely not doing auto grading. And I think another good point Adam is making is a whole bunch of small functions which do a little bit of checking here, a little bit of checking there, and pass around the values and temporary generation. And it's good to separate the functionality of what you're doing into small functions, and then they call each other through their mechanisms, and that way it will help you to debug. And I think that's the whole intent of modern object-oriented design, which is great. LOC complexity, or number of man-hour complexity, I don't have an exact measure of how much it is, but it should not be complex. If you're going on a very complex and complicated path, do check with the TAs. Both of them are very well versed, and they will give you tips of what may be going wrong to avoid any pitfalls. So, any other comments or words of wisdom, guys?
I can tell you that my concept classes, which are the ones that basically represent each Tiger concept, I have about, it looks like between 50 and 60 classes, and this was in Java, so every class has its own file. And of those classes, I think I only had maybe a handful, definitely less than 10, that had any more than 100 lines of code. Everything else, I'm looking at one right now that has 7, another that has 24. There's another that has 30. So they're all pretty short. And then I have about 10 classes that are just supporting, like I have a class for my symbol table, one for the symbol table container that gets passed around. I had to make a stack, stack data structure. So I would say maybe about 70 class files in total.
Okay, and this is of course uh, for phase one, right? Or is it phase one?
Phase one, yes.
Okay.
And this was also with the slightly more complicated type comparison logic. And when I did the project, we had the record data type that's kind of like a struct, like a C struct.
Yes.
We had more flexible type equivalence and computability checks that was not just based on named type equivalence. So there's a little bit more complexity in my implementation here, but honestly, not that much.
Right. That certainly can grow, especially the big difference between name type equivalence is much more simplified compared to the structural equivalence. The algorithms get much more complex in structural type equivalence. And yeah, I can see that. So this complexity, what these guys are experiencing or should be facing, is definitely on the lower side, I guess. Much lower side, because we don't have records and structs and fields. That means many less number of checks, many different subcases eliminated, and then structural type equivalence is a total different beast by itself. Name type equivalence is very simple because it's passed along through a label or a tag, and it boils down to tag comparisons rather than mapping of different fields and isomorphism between them and other complicated matters. So that's good. That should give you a good idea of where you should be. I would expect maybe 40, 50 classes there in this implementation from what you're saying, Adam, and in their implementation, and equivalent number of maybe LOCs, not more than 3,000 lines of code. Is that a good idea here or not?
Yeah, that sounds reasonable.
Good. So, okay. Thank you, Adam, for shedding light on this.
Sure.
And it always helps to hear back from somebody who has actually done it. Chow has not done this class per se, but he has delved inside LLVM, which is a very complex beast, which is a very different kind of beast, and which has a very different level of complexity. So we don't, of course, deal that with in this class. So. Okay, any other questions we should visit from Piazza posts or anything that any topic which is important for them at this point?
No. Alan, do you have something to say?
I guess the question was, Adam, do you have anything to say about any topic we should visit or anything?
Oh, sorry. No, I don't see anything else that's come up.
Okay. About Tuesday morning, 7 a.m. is the new deadline, and let's give them a few more couple of as till 29th as further revisions if they want to, but put a note there that they are strongly discouraged from extending it beyond Tuesday, um, and they should really start working on phase two at least by Tuesday. And we don't have any team. I think we talked about team issue, right? If there is anybody who is facing any team issues because their project partners are dropped and all for phase two, again, talk to both of them and the TAs, and they will assign you to another team right away. Or if you want to continue by yourself in phase two, then let us know as well. You now have complete phase two in front of you, so you have a knowledge of what amount of complexity it may have. So let us know, and we'll help you out there. If there's no other question, then I guess we're almost we still have about 10 more minutes, but we're pretty much done with the topics for today, and we might want to wind up in another 5 minutes if there isn't anything else. And we'll see you next week at the same time then. So I'm going to mute myself a little bit.
Sure.
Okay, so guys, I guess I'm signing off because I don't see anybody else on the Hangout and I don't see any other questions. Thank you, Adam, for covering some important topics today, and hopefully all these hints and a little bit of extension help everybody out. Do announce on Piazza about this recording because I think it's quite critical that they go over it, although they are not attended, many of them, because of maybe they are busy and doing some work or at perhaps at work itself. So do announce the recording on Piazza, especially important stuff about Project 2 is covered a little bit today. Project 1 is covered rather today, and we'll see you all next week at the same time. So I'm
Okay.
going to sign off now. Thank you.
Thank you. See you.